morning. Good morning. Okay, everybody hear me? Okay, good morning. Thank you for coming to this deep dive. 3 hours. We will dig indeed super deep into Cassandra. You had plenty of choice, so thank you for coming. I'm Cedrick Lunven. I'm leading the developer advocacy team at DataStax, Java geek, like most of you, I guess. I created 10 years ago now FF4J, so feature flipping for Java. It's a feature toggle implementation for Java. And I'm doing, of course, a lot of Cassandra, contributed a little bit to Jeepster, doing a lot of APIs, and lately I'm doing some SDKs and CLI with Java, compiling native. So if somebody told you to do some CLI, you should use Go, you can tell them Jay is working as well with Java. My coordinates, if you want to join me. So it's a deep dive, so it's not supposed to be a hands-on, even if I will do a lot of demo in front of you. You can do the same demo as me. All the materials are provided to you, and you have nothing to install. Everything is on GitHub. This is the link. All the instructions, step by step. And there you will have an IDE. It's called Gitpod, IDE in the cloud. And you can reproduce all the operations. You have nothing to install. It's web-based. So if you want to do that with me, go for it. So that's the plan for today. We'll dig into Cassandra. What is Cassandra? What is the underlying architecture? What is the architecture? And based on the architecture, we will design what should be the use case. Then connectivity using the drivers, executing a few statements, a few queries, going over the advanced features, synchronous, asynchronous, reactive programming, object mapping, and how to implement some Cassandra applications with Spring, Quarkus, Micronaut, especially on the data layer. I think that over the week, a lot of people will go deeper than me in those 3 frameworks, but still we will focus on the data layer, and we will still compile them in native. And also go beyond that because, no spoiler. So that's the other agenda. Okay, it's dense. We will do probably 2 parts, 90 minutes, with a break to have a coffee. This is what you can find on the GitHub repo as well. Okay, so let's start with the beginning. Intro to Cassandra, right? So, relational databases are great. You can do a lot of things with them. They are versatile. You can do OLTP, and you can do OLAP based on how you install them. You can do super fast synchronous queries, live data, meet the high SLA, very good. You can also do OLAP, data warehouses, complex query, data warehouse, data mart. But those kind of queries at the end of the days for business intelligence tends to take minutes. So in 2008, 2 engineers at Facebook needed this extra performance with a lot of data. Okay, with the volume of data, you tend to have your response time decreasing. And those 2 engineers at Facebook saying, no, we still need that response times. So they invented Cassandra. Cassandra is a NoSQL distributed database. Okay? You can install Cassandra on a single machine, of course, and you can expect to have between 2 and 4 terabytes for the machine and execute about 3,000 to 5,000 transactions per second and per core on 8, 16, 32 cores. That's already some throughput. But of course, you want to install Cassandra in a distributed manner, like this. In this architecture, there is no master. It's peer-to-peer. The nodes will communicate to each other using a mechanism called gossiping. And you will group those nodes with something called a data center or a ring. Okay, no master. So What do you want to do with Cassandra is those things, but I will explain each one of one. Big data ready. Wow, what a buzzword to start my presentation. Well, look at this. In Cassandra, I put back here a ring. In Cassandra, you store tables. You have a schema, and in the tables, you will find a primary key to ensure the unicity of your record, but also inside the primary key, part of the primary key, something called the partition key. It tells how the data is distributed across your ring. So here, if I take network as my column for my partition key, and I start save this table in Cassandra, this is what it looks like, even if I only have 10 to 15 records. So immediately, 5 minutes in, select star from a Cassandra tuple is not a very good idea, because you do a full scan of your cluster. So with 15 nodes, okay, but with what about 1,000 nodes, 2,000 nodes, 100,000 nodes? It could take a while. We even represent the network like this. So here, 2 rows will represent a single partition like that. This is what we do. So you group together what you want to retrieve together. And that's the key to ensure super fast performance with petabytes of data online. And I'm not exaggerating. Okay, linear scalability, benchmark for Netflix. With this database, if you need more capacity, add new nodes. If you need throughput, add new nodes. And this is one of the best use case. You have some huge volume and still want to request in real time. How much can you scale with Cassandra? You saw my t-shirt, while true scale with Cassandra. So last week we had Apache Con in Louisiana, and both Netflix and Apple shared about their use case and volumetry that they do have on Cassandra. And it was even so big that it was put on Hacker News and reached about the 10th position, I think, on Saturday, and I took the screenshot on Sunday, and it was already 30-ish. So Apple does have 300,000 Cassandra nodes. iCloud run on Cassandra. Hundreds of petabytes, over 2 petabytes per cluster. So that's huge, millions of transactions. I will let you read the slide. And for Netflix, yeah, smaller, only 22K nodes, but 900 clusters, so pretty good, 12 petabytes online. And it's not covering all the use case at Netflix, but 98% of the volume of data at Netflix run on Cassandra. So it scales. But there are some trade-offs, some things you need to know to make that stuff scale. So let's see today what we can do. So I told you in Cassandra, the nodes are grouped in data center or rings. In a Cassandra cluster, you can have multiple rings in a Cassandra cluster, multiple data center. You will install those data centers across multiple regions. You can read and write from every node, and data will be replicated by Cassandra for you, asynchronously. And we will explain how much does your client wait. High availability. So your record is available on multiple locations, multiple data center, and even inside a data center, the data is replicated. So of course, no single pool of failure. It's active, 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 active. Okay, no RTO, no RPO. And the client, the drivers, the one we will look at today, is smart enough to do the load balancing, the failover, the retry, the reconnections for you. So read and write performance. So you want to write very fast. Cassandra is known for very, very fast writes. And because it will come right in memory and back. And so at some point, data is flushed on disk. This is why the write is so fast. But still, every node will work. It's not a single master that will take all the writes and replica read nodes. Here, all the nodes are the same, masterless again. It's a tarball. You can install Cassandra everywhere. Super easy. Just enter, set up, you're good to go. So this one is a little pushy, I admit, but it's one platform, one database you can install on any cloud. Not the SaaS, not the PaaS, but just yes, deploy your nodes on any cloud, just Linux box, make that job a data center, and you can have them in the single cluster. So here you can have a single data layer, single database across clouds. So technically speaking, working. Now communication inter-cloud, okay, nothing is magic. There is a cost to pay for this cloud-to-cloud communication. You also need to do some peer-to-peers. But again, technically possible, no problem. This one is nice, vendor independent. It's Apache license. So this is a database that will not change the license anytime soon. It's Apache 2, and we will stay Apache 2. So in a nutshell, if you want to explain someone Cassandra, why would you use Cassandra? Well, first, linear scalability. So if you have a large amount of data and still want real time, that's a good candidate. High availability, data distributed everywhere, low latency, always on, use case, and global distribution everywhere. So that's the promise. And today we will see what are the constraints and the rules you need to follow to achieve those kinds of performance. So Cassandra 4 has been released last year. We were waiting for this version, for 6 years already. And you see by the size of the rocket how much time we had to wait how many features are put there. 4.0, and still it was used in production immediately by the big web giants that I just shared before, Apple, Netflix, Instagram, Uber, and so forth and so on. So today the demo we will do will be on Cassandra 4.0.6. 4.1 has been released in beta last week. We expect a release by the end of the year. And 4.2 will be next year. Maybe a 5.0 if we introduce some breaking change. But again, I will come back to that later. Okay, 15 minutes in. A lot of slides already. So let's the Cassandra cluster. So for today, here you have my slides. First screen here, you will have my GitHub instruction, like I told you here on the left part. And on the right, this is my IDE. Here I do have some Gitpod. So let's look at the instructions. So the material, the slides, everything is provided to you. You can also run the same demo here prerequisite. You will need Docker, JDK 7, Apache, Maven, and Graal. And the first things we do, actually, we'll do that here. First things we do, we start in Gitpod. Okay, our ID in the cloud. Okay, it will start, it will package everything. So it's starting. Let me do my setup. So here we are. So is it big enough? This guy is still starting. All right, so let me show you a Docker compose here. Okay, as I told you, we will use Cassandra 4.0.6. We open the port 9042, that's the default port, 2 GB to run Cassandra node. Okay, in production, you would probably use 4 to 8 GB in RAM. So here I will deploy a single ring, single data center. It's called DC1. And when you start a Cassandra ring, I told you there is no master, but still one of the nodes in a ring is called a seed. That's the one you want to start first, because the others will use the IP of the first to join the distributed cluster. So that's the cluster name, and this is how the data would be distributed. You can tweak Cassandra to tell how the data is distributed. Okay. So here, let's see. Yep, it's still packaging. Okay, it's doing things. It's doing the setup. What we will do first is Docker compose. So back in the Docker compose. So that was our seed. Second node is regular node. We'll use the seed here for the link, still DC1. And here, I just get rid of the volume for the demo. I will scale my node, so no way to provide dynamic volume in Docker. So during the time it starts, at DataStax, we provide a way to deploy Cassandra in Kubernetes, an operator, but way more. It's called Cassandra, Kubernetes plus Cassandra, providing not only an operator, but also all the tools needed to run Cassandra, the monitoring, and the maintenance operations. Okay, so let's see, where are my terminal? Here we go. Okay, so I'm going to the setup. Okay, and starting my first node. Okay. So this is the node, the seed is starting, and then we'll start the first node. Little trick, here I add a tempo of 30 seconds to run, to start the second. So rule, in between two node start, you need to wait 2 minutes, here 30 seconds because it's empty. When a node will join the cluster, the keys will be redistributed among the nodes. So you need to wait in between. Okay, so it will start and I will have my little guys ready. Okay, Docker PS compose. Yep. Here we go. Okay, running. So then what I'm doing here, I exporting the container ID as an environment variables here for the seed nodes, because I will connect inside the seed nodes to run some command and see what is the status of the cluster. So to do that, I'm using a tool called NodeTool. And I will do NodeTool status. Let me close Docker Compose for now. As you can see, as of now, I still have a single node here. So let them start. It's coming. Okay, plan B. I have it running here. Docker PS. All right. So here it's running, right? So I use the instruction. I start the 3 nodes, and then I scale node 2 just to get my 3 nodes. Okay. When I do have that, I can insert my seed nodes, not to execute node tool, but to execute CQLSH. CQL stands for Cassandra Query Language, and there I will create a couple of things for the demo for today. So here in CQLSH, I can contact the system tables to get the cluster name, the DC, and the IP of my seed nodes. This is local, and I can get the IPs of my peers. Okay, here we have. All right. Here we will create some key spaces. Inside a database, you will have multiple key spaces. Those are kind of Oracle schema. The best practice is to have 1 key space per application. So here I will create them all at once, just to gain some time. So Devox, drivers, Spring, Quarkus, and Micronaut. This is everything we will do today. Okay, so a few key spaces are created. So you might think, oh, what about here the network topology? We also had the same in the Docker compose.yaml. So in a data center, in a ring, you can save the node or declare the node in some rack, hardware rack. Cassandra will be aware of this rack distribution and will try as much as possible to avoid having the replica of the same data part of the same rack. The idea is if you lose a rack, you won't lose multiple replica of the same data. So in AWS, you will define a rack per AZ, for instance, just to avoid losing multiple replica if you lose an AZ. And durable writes. I just told you writes are super fast in Cassandra because when someone come and want to insert data in the node, it will be written in memory and back. And you might say, and you have to say, what if the node goes down and the data has not been flushed on disk, and you're right. So this is why we put the durable write. So doing so, and you should do so, when the data is written on a Cassandra node, it will also be written in an already open file called a commit log, and it will just happen at the end. So if the node crash, when the node restarts, it will read the commit log, re-execute all the mutation just to get back the state in memory. Okay, and DC13, we will come into that in a minute. But hey, so here I do have a couple of key space starting with Devox, as you can see here. And we are ready to go. The cluster is up in my machine. What about this guy? But I will probably not. Okay, so now we have our 2 nodes. And if I want to scale that guy, and I will let that running. But I won't keep my 2 cluster and doing the operation on 2 cluster during the 3 hours. Okay, so we started Cassandra, we scale Cassandra in Docker. What about the drivers? My biggest challenge for today is that. So this diagram comes from the survey Stack Overflow 2022. I show you Cassandra is super powerful and can scale. So why so many developers would like to change? See, the dreaded is 59, way too high. And I'm sure that this is because people are not aware of how to develop, how to implement a good app on top of Cassandra, and try to stick using the relational methodology, the GPA kind of work. And of course, they got frustrated because it's not how you should work. Okay. So this is our 3 nodes. So we have DC1 seed, node 1 and node 2 running, and the application will host your drivers to connect to all the nodes. As of today, in Docker, only one node will be used, 9042, to get our request. The drivers is inside your app. So the drivers, okay, no surprise, obvious, will ensure first connectivity. But in that connectivity, I told you, reconnection, retry, connection pooling, else check, authentication, SSL. So it's not your job in the app to implement a thread pool to handle all the parallel connection. It's done at the driver level. You will use it to execute any kind of queries statement using Cassandra query language. And Synchronous and Reactive are supported. And once you execute your query, of course, you want to parse the result and map your objects. But we will see that into many details. So, drivers. If you have used Cassandra before, maybe you had, we used to have two sets of drivers. DataStax is famous to implement the Cassandra drivers. We also contributed a lot to the open source project, of course, but we actually own and maintain the most in use Cassandra, Java Cassandra drivers. So two sets of drivers. One was for enterprise-ish product, DataStax Enterprise, and the cloud distribution. And starting 4.5, you only have one drivers. And so everything you will see today will leverage on this driver 4.5. I mean, today we will use 4.15, but 4.5 released in 2019. But if you are stuck in 3.x, I provided 15 Java sample using 3x and 4x and explain how to migrate easily. So here, 4.5. So in your app, you will connect to the ring. You will define one IP, one node. It is a contact point. During the first connection, the node will come back to you with the list of all the IPs of all the nodes, and also a description of how the data is distributed across those nodes. So as soon as the connection is established, the driver will initialize a connection to every single node, TCP connection. And at the drivers, you will do some else check, load balancing, retry, reconnect. So as the drivers is aware of the distribution of the node, of the data, when you execute a query, the drivers will pick one of the replica that will get your data. So one is enough. Recommended is, of course, 2, resilience. Just for this very first connection initialization, it's better to provide 2 contact points. Finally, and it was introduced in drivers 4, I told you in a Cassandra cluster you can have multiple rings, multiple data center. So you should provide the local data center, the one you want to use and reduce the latency. Your application should work with a local data center and only fail back to a distant and remote data center if the data center goes down. But if the data center goes down, you probably have more issue than just that. But the application should use a local data center to reduce the latencies. And I show you that to show you a little bit of code about the drivers. Okay, so this time, let's see. Okay. All right, so here, using my ID maybe. So here, first project is lab drivers. If you go to the POM, I importing the drivers, version 4.15. Okay, and I'm using DC1 as my data center. So first code that I will show you today is how to connect. Okay, and here you go. So you will work with an object called SQL session. It must be a singleton for your app. I told you it's stateful in handle connection pooling and else check for all the nodes. So it's heavy. So don't try to implement or create multiple. Okay, you should have one. And here, so the contact points you define like this, and you can build and you will get your SQL session. But of course, what you want to do is provide your local data center. Okay. Let me go back here. Of course, what you want to do is externalize those constants. That's obvious, right? So you can have an application file called application.conf in your app using the type-safe structures, and all the keys will be defined here. Contact point, session name, session key space, and here's some advanced properties. So this file is important. Even if you're running a Spring app, Quarkus, Micronaut app, if you got this file in the class path, the drivers will detect because the three are using the same drivers, okay? It will be detected and those fine-grained keys will be used because, spoiler alert, if you are using an abstraction framework, of course you will get some nice couple of keys in application.yaml, but you lose all the hundreds and hundreds of properties that are available in this file. So, long story short, here I put back my contact points, my key space, a couple of timeout, the DC name, and now our SQL session can just be written SQL session.builder.build. Aha. And what's doing our test? It will just list what are the nodes of our cluster and just say hi. Okay, so let's see. And remind me later. Okay, not the good time to do it. Okay, so and here we have our two test passing giving us our nodes. So, connection, fine-grained setup of the connectivity. Very important across all the application. Okay, all right. Connect and drivers configurations, done. A couple of slides on configurations. So the load balancing, default load balancing, so I told you the driver is aware of where the data is, and it will load balance across the different replica holding the same data. So if you select always the same data, it will load balance among the replica holding the data. And now comes the question, how those data are distributed inside one data center. This is what we will see right after this. Retry policy, okay, it's implemented at the driver level. Reconnection policy, default is exponential reconnection policy. So try after 1 second, 2 seconds, 4, 8, 16, and so forth and so on. Okay, so important data distribution. Let's start with the slide we had before. Single table, data is distributed among the nodes. Okay, right. How do we know? How does Cassandra know that forest should be there and this guy car should be there, and how the distribution is made? The partition key is encoded to an integer up to 2 to the power 64. This is what we call a token. Each node is in charge of a range of a token. So the distribution is done using murmur3 hashing, so I have to have a balanced and well-defined distribution. But you can think about modulo for today, the mathematical modulo formula to ease the comprehension of today. Also for today, we will think about, let's have an overall range of 100, even if the real number is 2 to the power 64. And let's pretend that those token range are owned by different nodes. And here I put some color code. It's a simplification. In reality, each node will have something called virtual nodes, just logical split, just to have the token range even more distributed. Let's keep it simple. This is what it is, right? If we consider only 100 rows, and the token range are distributed like that. So data is distributed across one ring. Okay. Data is also replicated inside the ring. I keep talking you about replica. So here if car is here, and we said before that the token from car was 8. So 8, okay, is in this node. But when you create a key space, and we already did a couple, you saw that for each data center we provided a number. It is the replication factor. So 2 data is in 2 nodes, 3, and so forth and so on. Recommended value, 3. An odd number. And you will see very soon why. So recommended 3. You can go up to 5 if you are in a hostile environment when you can eventually lose a lot of node, but most of people are using 3. Okay, so here I come. I'm a driver. I want to write car in my ring. Token is computed by the drivers. It's 8. Drivers is token aware, so it will know exactly that those 3 nodes are candidate to get that right. So we'll pick 1. This node becomes what we call a coordinator node for the request. It's not a master, it's just a coordinator node for this single very request. So, okay. The coordinator, of course, is aware of the 2 of the replica holding the same data, and using gossiping, the data is pushed to the replica. Okay. So with this, no master, and the data replicated 3 times, you can lose a node. You can restart a node, upgrade, whatever. You can totally lose a node. If the node is lost for less than 24 hours, the coordinator node will save the data locally in files called ints. The principle is called int in handoff. And when the nodes come back online, it will get updated with all the mutation that had happened during the time it was down. So this is why we say Cassandra is self-healing. So now, of course, question, what happens if the node is down for more than 24 hours? Then it's better to declare him decommissions and introduce a fresh one just for him to redistribute the key. It's probably even faster than trying to get the ints coming from all the nodes. So when you create a key space, and we did that, you can make your key space live in one data center or multiple data center. Your choice. So for sensitive information, maybe you will have data center only in your country and for public one distributed across multiple locations. And here the number is of course the replication factor. Okay. So who has heard about the CAP theorem here in distributed system in the room? So, okay, not so many. So CAP theorem, or Eric Brewer theorem, stated that in a distributed system, so something living on multiple machines, you cannot ensure at the same time consistency and availability if you lose the network. That's an English way of saying that. Partition tolerance is 2 nodes inside your distributed cluster cannot communicate to each other. Okay, network down. What do? Do we ensure consistency? So the system is down until we are sure that all the replicas have the same data? Or we focus on availability and say, okay, you may not have the very last updates of the data, but I will reply to you. So what do you think? Cassandra is AP, availability partition tolerance, or CP? A lot of people will told you that it's AP. Actually, it's you to decide. When you insert some data or you read some data in Cassandra, you will position a value called the consistency level. And it stated how much time you made your client wait until he got acknowledged and consider that the data is valid. If you are on a single data center, single ring, you can use one quorum all. To be honest, any 2, 3 are not really in use. So 1, it's the fastest. As soon as one replica gets acknowledged, and probably the coordinator node, tac, you move out. You got your reply super fast. Quorum, you want the majority of the node to get back to you. And this is why we want to have an odd number to get the majority of the node. If you put a replication factor of 4, then you have to wait for 3 replica to acknowledge you, and it's slower. So 3 to get the majority, 2, we're good to go. In a multi-DC, also you can choose. You can decide to work with local cluster, local data center, just to increase the latency, just to have the better latencies. So local quorum, the majority of the node inside the local data center will get you back. Each quorum, you want the quorum everywhere. So the more you increase the consistency level, the more consistent you become, right? And at some point, if you say all, you are fully consistent. Because you want every single replica to acknowledge you, getting the value, you are sure to get the latest. But what the CAP theorem told us, if you add some consistency, you lose availability. And so all is not recommended at all. Maybe for one mutation in the morning when you want to, I don't know, write the inventory or something like update the data once in the morning. But after that, you should and will use always quorum. Okay, so the replica are not in sync. So are you sure you will get the latest version? Because it seems to be weird if somebody writes with one, what about the 2 others replica? They will be updated by the system, but you are not really sure if they will be updated in time. So, question, what will happen if somebody writes and reads the same data at the same time? So what about race condition? So let's have a look. Client A in blue, so replication factor is 3, and here I will write with quorum. So I pick some data, pick my coordinator node, for some reason, coordinator node here was not a replica, but nevertheless, it will write the data in the 3 replica here. Client is waiting, first acknowledge, second acknowledge, okay. The mutation is complete. What about the node? It will be updated, of course, but maybe 2 milliseconds later. Actually, it did not acknowledge. So we cannot say for sure that the 3rd replica is also updated. So what about now client B reading the same data? We know that those 2 nodes are updated and the 3rd is not. Okay, we'll ask for the 3rd replica to response, and this time, of course, otherwise it's not funny. Only the wrong one reply in time, and so now the coordinator node got 2 different response from him because it's from it. It's a replica, so he will have its own value, and value coming from the other node. So in Cassandra, the last write always win. And so the client R will get acknowledged with the proper latest value. Because each time, one updated replica will be part of the read. So how do you make sure that you have that all the time? This is what we call immediate consistency. That's the rule. The consistency level when you write. So here it was a quorum, so the majority was 2, and when we read same, it was 2, and it was strictly bigger than the replication factor 3. When you apply that rule, you are sure that you get the immediate consistency. Okay. Yeah, it's a lot of slides, but soon we will move more into code. So let's see. So here we scale the cluster, we got these. Okay, data distribution and get starting with keys. And yeah, after that, more code to go. What about this guy? Jeez. Nice, that's yeah. Okay. Okay, after that, more code. So, getting started with keys. In Cassandra, you have multiple key spaces. Okay, I told you that key spaces hold the replication factor. Okay, now you know. You find some tables, you already know. Tables are organized by with some cells, rows, columns, but also partition key and partition that will code how the data is distributed across the node. There is a schema, so it's NoSQL, but it's not schemaless, okay? So you have a schema and it's enforced, you need to comply with it. Okay. Partition key, very, very important. The partition key will code how the data is distributed. So when you execute some queries against Cassandra, partition key should always be in your where clause. Because if you provide a partition key in your where clause, well, we will immediately go to the proper node, holding all the data, and you get back all the data. If you do not provide a partition key, we will have to do a full scan cluster to see if the data is there or not. So here, this is a table coding for an IoT. We have some sensors recording some temperatures over time. And you might think, how do we code a table to store that? you might think about having just the sensor the partition key. Like that, all the data of a single sensor will be in the single node. And as we tend to draw some temperature over time for one sensor, it could feed our use case. A partition key could be composite. Here you have two columns, so both the sensor and date. So here date is YYY, months, day, just a day. Okay. But partition key alone does not ensure unicity. It's not enough for a primary key. It could be. Sometimes a partition key and primary key is a single column and a UUID, and we're good. Then we will have single row partition, but that's okay because we kind of retrieve data by ID, create, read, update, delete, and for that it's good enough. Clustering columns are what you need to complete a partition key to be a real full primary key. So clustering column will be there to sort the data, execute some inequalities, range queries, so ensure the unicity. So here, a couple of examples of invalid primary keys. So the first one, sensor, not unique. Each time a new value will come, boom, wrong, you override the previous one, not what you want. Sensor and timestamp, considering that one sensor will get you only one value in 1 millisecond. Yes, you can. Okay. But what is the query you want to do? You may want to query per date. Just provide the date. You could do inequality. Yep. You could do a range, but it's not as convenient just to request on the date. But it's still valid. The third one, it's not a key, right? Do not put the value in the key. And the latest here, the sensor, date, timestamp, could be a good one, not the best one here. The best one is here in the table, and we will see that. Also, the clustering key, you will define ordering of the clustering key. The data is sorted on disk based on this ordering. So the place of the clustering key in the is important. You want to sort by this field and this field and this field if you need multiple sorts. So finally, the primary key needs to ensure unicity, combining both the partition key and the clustering column like that. Okay. So this one was good, right? I told you, all the data for a single sensor is on the single node, so you can query. You can do the range query on the timestamp. But here we have an issue. Over time, more and more data will be saved in the same partition. You will have that partition holding all the value for the sensor, getting bigger and bigger and bigger. And we have some rules in Cassandra that a partition should not go beyond 100K rows or 100 megabytes or 10 megabytes per cell. So this one, even if technically correct, at some point it will not scale. You want to keep small partition. And to do so, you will introduce dedicated column to split the partition into chunks. So it's called bucketing to keep the partitions small. So this is why here you will get all the values for the same day on one node, but it's kind of a fixed size. The day after, the partition will change and your partition stay small. And this is what here I was seeing. Okay, during the labs, I will show you some SQL code, Cassandra query language, and for those we will use one key space called devox. And then I will show you the same using some Java code. And for the Java code, I will use the key space devox drivers. Just I put this slide to avoid any confusion. So I do have my IDE with the drivers and also have SQLSH, which is a shell I already showed to you. Okay, so now let's dig more into some code. Okay. And yep, what I need is more SQLSH. So here it is. So here, connectivity through drivers, data modeling, done, data modeling. Okay, all right. Describe key spaces. So we do have our key space devox that we want to use here. Desk table, no, we want to use devox and only then desk table. Okay, empty as expected. So here, city by country. So that's data modeling rules that we will also cover a bit later. So by country, meaning that country will be a partition key. So multiple cities from one country will be in the single partition. Group together what you want to retrieve together. So here I go. Get my tables. Okay. Now, what if I want to do the same in Java, right? So this is what we will try to do stuff with SQLSH, then try to do the same in Java. So to create some, and I will probably need to do that to have them side by side. So now if you want to create some schema in Java, you will reuse your SQL session that we just created before, and we will, I will pick one of those. You will execute a statement, execute a query. So this is the query you want to execute. But best practice, what you want to do is define and design all your table names, column names as constants in your app, because if you change the name of the column or of the table, you have to do it once in the constant, and you're good to go. Or if you drop one column, you drop that column, and you will see some compilation error across your code, where easier to detect if what is impacted if you change one of the if you change the schema. So best practice, little trick like that. I mean, sometimes most of the time I use an interface, because interfaces are public static, of course, by default. So here I tend to put all my keys, column names, and reuse that everywhere. So here you have a query builder helping you building the statement. Here's a schema builder, and I will execute that. So create table user, so this is what it looks like. Create some table video, and so forth and so on. And we will dig into all the little details of what you can do with the data modeling. So here, see, create. So I will do it once. I will apologize. In the test, you will see now, most of the time, there is no assert validating the test. So, you can send me tomatoes now, but yeah. Here you go, and you will see how to create those. So should create. Okay, so it's coming. So even to create schema, SQL session.execute, and you create your schema. Later in the presentation, I will tell you never do that, but at least you can do that. So now if I go here and use devox drivers, and describe tables, here they are, of course, and you can always do describe key space, and maybe I should show you that now. Oh yeah, key space, yeah. Jeez. Finally. So why should you create the key space with Java or Spring or Micronaut or Quarkus? This is because when you create a table, this is what you create with the Java code. So good. And this is what you miss with the Java code. And this is quite important. So for instance here, default TTL, default time to live. When you insert into Cassandra, you can have a time to live, and so the data will be deleted by itself without you having to delete it like a cache after after the time. And the code does not provide you. So the best practice here is define your schema on a dedicated DDL file and think about this metadata. What about the default time to live? And what about compaction strategy or GC grade second? Some keys important in the metadata here. Okay, so I created a few tables here. So now what about, so let me go back to DevOps So here, inserting a bunch of cities, okay. All right, I can select star, again, never do that. I'm doing a full scan of my cluster just to get that table. Okay, so here, let's execute a few queries and add a few queries. So select star, we did that, list all the French queries. It's also kind of a small game. What should be select from city where? Yep. Kind of. Yeah, yes. Okay, good. What about in? Okay, that's a sample in for Canada or Belgium. So in is not a very good idea. In, you doing the coordinator node will now be in charge to select for CA and then for select for DE. And you move the load from the client to the coordinator node. Here we are asking the coordinator node to n+1 select. What you want to do instead is at the drivers or your app level, do 2 requests in parallel and fire the 2 requests. Because in can lead into so many issues. In next version 4.1, we will introduce something called guardrails to limit some invalid usage of in. So by default, 5 elements in, you get a warning, and 18, you get an error because it's working, but you should not use it. So now Brest, okay. So now let me try select from city where city equal Brest. Is it okay? Expected error message. I execute a request in my table, but I request on something that is not the partition key. So the only way to perform the query will be to go ask every single node to see, do you have it, do you have it, do you have it, and it will be slow. So the way to make it succeed, that also will be forbidden in 4.1, is to add allow filtering. And now it's basically saying, okay, I know what I'm doing, do your full scan cluster. Why I show you that and all these stuff if you're not supposed to do that? Well, the reason is you are doing it with the framework you are using without noticing. Like the allow filtering. Oh, it's just an annotation to add in your code and now your query is working, right? It's not how it should be. Okay, select inequality. Here, city is the clustering column, so I can do some inequalities as long as I provide my partition key. Example of updates. Always provide the full primary key to do your update because you want to update a single row. Okay. And if let me get pressed again, should have been updated, right? The population should have been updated. Okay. It's updated. Let's insert, okay, an existing value in the table. What will happen? Changing the numbers to, I don't know that. Integrity constraint, primary key already exists. No, it's working. In Cassandra, every insert is an upsert. So this is why we can retry, because those are idempotent, and there is no integrity constraint. So that's your job to ensure integrity. You have something called lightweight transaction to help you with that, but be aware that in Cassandra, no joins, no integrity constraint. And so if you want to delete a row, you can delete a row, or you can delete the full partition. So here I'm deleting the whole partition. So best practice is always to delete as much as you can, because under the hood, Cassandra does not really delete the data. It will add something in the table. It's a marker stating that this record, this partition, does not exist anymore. It's called a tombstone. And once every 10 days, there is an administration task that's running under the hood that's calling a read repair that will remove all these tombstones. When you execute some read and you scan a wide range of tombstones, because you can get a warning. So if that happens, think about reducing the parameter called GC grace second to make the read repair running more frequently. But anyway, insert delete is not insert delete like kind of a queuing system. It's an anti-pattern for Cassandra. There are plenty of messaging brokers to do that. Pulsar, for instance. Yeah, so queuing is considered an anti-pattern in Cassandra. So more function here you can group, doing some average, a few computation. You can group by city, doing some count. And when you need to clean a table, avoid to do delete, because if you miss some space and do delete, you will have even less space. You will just add tombstone. So truncate is the way to go to delete that. Okay, so a couple of statements, SQL. So now what about the code? And again, I take sometimes on the drivers and not so much time yet on Spring Data, Quarkus, Micronaut. Because first, the drivers is used in all these apps, and you can always have access to the SQL session. So you know how to use the SQL session is kind of the way to open the box and do it by yourself if you are stuck with the abstractions. And long story short, the abstraction are masking you some capabilities of the underlying drivers. Okay, so what about statements? Maybe this one deserves a bigger one. So SQL session.execute. Okay, obvious, here it is. You will execute, insert that. Okay. Now, I mean, you are probably doing some GDBC, SQL GPS, so you are open to any XSS SQL injection, so never do that. You want to externalize some parameters, but still, you know, it's working. Every string that you execute under the hood is a statement. Okay, and this statement is super important because this is at the statement level that you can define some important properties like consistency level, something that you may not be aware that it exists. I execute queries and I'm good. I think the defaults are using local quorum, but it's not always the time. So best practice, you should enforce the consistency level in your queries because, I mean, you know, you should know which queries should be super fast and you do not care about the consistency, like IoTs, local quorum, I mean, consistency 1, good enough. So every queries you execute is a statement. A statement also have idempotent true, paging size, execution profile, and more stuff that I cover later. But yeah, statements hold a lot of metadata that you might not be aware. So, okay, here, query is a statement, done that. Okay, you want to externalize the parameter using either a question mark, like here, and then you add position value one by one, or you add position values and you put them in one go. You can also use labels, and here EFL, 3 values, one by one, or the same with set values, with immutable map over here. Okay, so that's my first test. And second test, here I using the query builder. Remember, I told you externalize your constants. So here using the query builder, this is probably what you want to do. And instead of heap rolling value, you are using query builder.literal to give you a value to your statement. Okay. And now, before executing your statements, you should prepare them. Preparing a statement is actually validating the syntax, the colon, the name, the type, everything that will take a while in your queries to execute. You can do that at startup time. At startup, you prepare your statement. And then when you execute your statement, you have just to provide the prepare statement and the parameters. And under the hood, this is exactly what happened. When you prepare the statement on the server side, the statement will be held in cache and get the prepare statement ID returned back to the client. And so when you execute a statement, you put back just the prepare statement ID and the values. And just with that, 20% performance gain. Yeah, you don't have to validate the syntax of the query anymore. Spring Data only introduce the prepare statement after 3.2. Spring Data 3.2. Okay, so let's try to execute the test. And again, everything that I do here, if you are more the type of people who like to do the stuff me, remember Gitpod is there too for you to do the same. And here we go. Okay, so we are prepared and execute a few statements. Okay, we're good to go. Yep. I think I was here. Now what about create, read, update, delete? Sample of statements, right? So let me here close most and look about the prepare statements. Okay, so create, read, update, delete. Okay, repository, we are going there. But here for now, let's reuse the SQL session and work it. So here, okay, I do not put some asserts, but at least I did here before all as a static and prepare the statement once to reuse them later when I do create, read, update, delete. And this is the kind of code that look like in real apps when it's after set properties, post construct, you might prepare some statement if repositories cannot cover what you want to do. So you prepare statements at startup and you're good to go. So here again, we've seen these, create table, nothing new. Truncate table, first time we are seeing is just session.execute query.truncate. So nothing special here. And the prepare statement, here what I'm doing is SQL session.prepare query builder insert into. So this is what I'm doing all the time. So SQL session.prepare query builder. Okay, and that's the creation, that's the prepare statements. Okay, all right. Keep looking. So create. So yeah, just thinking if I want to see something, because here it's the create user is insert into, blah, 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 insert into. Here we have a select from, delete from, select from. So now when I'm moving over my different tests, here, create statements, update statements, it's just invoking my function, right? And exist user, okay, this one is actually interesting, even if we will see that after the break. I executed select, here the exit, so, no, exist statement, exist statement. Okay, exist statement, here we are. So select from just the partition key, where user ID, email egal, so searching partition key, searching by the partition key. And here to see if something exists, I execute the query, but I do not parse the result. I just, hey, how many results will I get? And I get available without fetching. So could be also useful for paging later, but I can test an existence by just reusing the metadata of the object return. It's a result set, and we will see that after the break. Okay, should update delete thing? Yeah, not. I mean, that is just the purpose here is, for you to go back with this working code, mostly. So indeed, after the session, you're coming back with all these apps and code working and could be used as a notebook for your future applications. So probably no big suspense here. I tend to test a little bit before. Okay, here we go. All right, all good. All right, 5.4, advanced data type. As of now, we worked with scalar. var, text, int, boolean, all kind of scalar, easy. A couple of things, maybe we, let me go back to SQL, I guess. It's more convenient in SQL to execute those. So here, UUID. There is no integrity constraint, and there is no sequence. So how do you create a unique identifier without blocking the nodes? We are in the distributed system. We are thinking about speed, speed, speed. UUID is the way to go. So a node will generate a random UUID and write data in there. So super useful to be used, super useful for primary keys and ensuring unicity. How to make sure that the record is unique without synchronizing nodes in between. There is also something called time UUID. It's a UUID that will also encode a timestamp. Like that, you can order those UUID by creation date. Set. Okay, so here a table, I have a couple of movies. I insert 2 movies in the table, and then I add the column productions as a set. So it is what you expect, right, as Java programmer. It's collections of objects, not sorted, and unicity is ensured, like a set. So which is cool with this set is you can just add something in the set, just with update set with plus. You can drop. So there is no joins, but when you need to do one to many, if the many is a single value, well, you can add just a column called a set to hold those values. Okay, list, same, what you expect here. So I'm reusing the table user and I'm adding a column list. So list is a collections of user. List is a collections of data ordered. I mean, keep the ordering of insertion, and you can access the data by the index. Okay, so get list bracket 0, bracket 1, and you can exactly look what you search what you are looking for. Use set as much as you can. It's faster when you access some data list using the index. You are doing a read before write. So why Cassandra is so fast? It is because when you write some data, it just doing it. There is no check before. Just write the data. As soon as you need to read before write, this is how you need to start questions. So we will see in a minute, lightweight transaction, or here like that, you need to read, because if you access the list item 3, for instance, third item of the list, Cassandra will have to read the list, check if the third item exists, and only then return it back to you. So it's costly. So using the set, if you can, is recommended. If you don't need the ordering, go for it. And map, okay, map, as again, expected. So key values, key set, value set, and here you can directly add some keys, update sets here. So you just cast and key values. It's not known enough that you can have these one-to-many features enabled inside the table itself. Okay, UDT. You can create your own type, your own user type. So there is a schema, so having some nested type inside the table can be useful. Like JSON-ish. So here I create a type address, provide my own attributes, and then I can add my address as a colon, type address, and using the user now I can directly update the structures. So here it's indeed kind of doing nested types inside the tables, totally working. And you can then only search the UDT. So here the select, I only look for UDT stuff here. Address.street, address.city, address.state, like it was columns. So of course I'm coming to insert JSON with this kind of structures. It's working. You can insert JSON and provide users having first level attributes and UDTs, and you can also have as many nested type as you want. You can have UDT of set, of UDT of map. It's working. But it's not what Cassandra is meant for, because there is a schema and you need always to fill the, you need always to match the schema. So if you want really to work with JSON, use a JSON database. Or if really you have to store JSON in Cassandra, put just a text column. Don't try to reinvent the wheel. And I think let's go with the Java set list and map now. Here, number 4, set list and map. Okay, so same create session, truncate, prepare the statement. Yet get my DTO mapping my tables. And here, execute update, append set element, remove set element. So directly provided in the query builder. So sometimes you don't really know. Also, when you insert some list, you just have to say set list. Here provide it's a list of integers. Here it's really a list of integer. Okay, it's just a POJO, a set map, and here you provide the type of the keys and the type of the object. And here the object is actually a UDT. So here if I create the table video, just for you to look, this is what the table looks like. So in this table video, I do have a set, a list, a map of video format. And video format has just been defined above here. It's a UDT. So here, okay. So why I show you that? Because here we have this keyword frozen. Frozen means when I will save this data into my database, I will serialize the UDT and save the UDT as a single value to speed up and to avoid any more tombstone creation. So this is why here you saw I just define my UDT and I simply can insert my UDT over here. Just thinking if I have something special to say about list map UDT, probably not. Let's go run as unit, and I will keep list map tuple set UDT counters. Just looking. Okay, here we go. Okay, last, and I think we will do a break for 10 minutes. It's 90 minutes in. Counters. You know about UUID now, but what if you need to count stuff? No Oracle sequence, I told you. What we do have in Cassandra is something called counters, distributed counters, not easy to do. So with a couple of limitations, but here this is how you can do. Super fast, but not idempotent, because now when you update this counter, the only updates that you can do are increment or decrement. And so incrementing is not idempotent. If you retry an increment, you increment by 2. But still here some movie stats with 2 counters, and you can move one of the others. So pretty useful to keep tracking and stats. So like Mythics, using that to track the views and match that you might have. So here's the counters table and how to use the counters with updates plus and update minus. In counters table, you will not do insert, you will always do update. So here I create the table, see, and the first things I'm doing is not insert, it's update, like that. And let's do the same in Java and we're good to go. So here, create table video views with 1 counters here. This is the create table. And if you want to execute some statement here, increment, query builder.update, increment and decrement. And you have the full-blown increment, decrement to use with the counters. Counters that are barely exposed in the repositories of the framework we are using. So do not reinvent the wheel. They are there. Just use them. And I think I will do a 5 or 10-minute break for everyone to have a coffee and go back with JSON. Just looking at the agenda. 15-minute break. And we will cover more data modeling and the usage of the driver in Spring, Quarkus, and Micronaut with everything we learned this morning. So you already might tell that those frameworks are not telling you the full truth or show you what you can really do. Okay, so thank you. We're back. We were in the middle of advanced concepts in Cassandra query language, and we were discussing about counters. So after counters, now that we have seen that in the table you can have list, set, map, and your own structures called user-defined type, of course you are tempted to use some JSON, because now you have a nested type inside the tables. And here we are seeing again the same table I was using with Java, with set list map over here, and I will use that here in my SQL. Okay. So a couple of things here to notice. You can insert like Cassandra query language classic, providing the syntax to insert into set using curly bracket, square bracket for list, and here for map, kind of very looking like already a JSON. But for any tables, and not only the one with some nested type, you can actually directly select JSON from a Cassandra tables. And boom, you get the result as a JSON already. So it's not enough known even by Cassandra users, so that's unfortunate. You can also insert JSON. So instead of, sometimes you get a JSON, you unserialize, you map with your own type, and you save. You don't have to do it. You can select JSON. What about the type? Well, Cassandra will check the types for you, so you'll get the error if something goes wrong. Believe Cassandra for that. It's not schemaless. By the way, JSON itself is not schemaless, it's just validationless. And here, as usual, I have the same code available for you at Java. In Java, so here I was quite bulk. Insert into and insert into and insert select, providing the JSON keyword each time. So here it is, insert into JSON, like that. Yeah, the drivers do not provide you great things for JSON, so just go object, JSON, serialize, write a string, and put it like that. Also, looking my code, I say, oh, geez, a text block would be so much better now using JDK 17. Still some update to do in that code. And so I'm executing some stuff with my Java code. Here we go. Okay, should use JSON. Yes, I select and I insert with JSON. Super happy. So now, advanced concept. Okay, advanced-ish. Now we have covered a lot of ground already. We can dig into more Cassandra specifics. First specific is a batch. You can group multiple statements inside a batch. So here, chopping cart, having cart ID and item, so very obvious. You begin a batch, you insert a couple of statements, and you apply the batch and make sure that your statements are executed. Here we go, executing, and we get 2 items in the shopping cart with 1 batch statement. Okay, great. Let's do it another one. Here it was good because it was in a single partition. If you look at my table, the partition key is the cart ID. So when I insert 2 items in the same cart, I'm using two mutation in the same partition. But let's say now I have the same data duplicate in 2 tables. Like, unfortunately, I mean not unfortunately, but like most of the case, you have 2 access patterns to the same data. You want to retrieve the ratings and providing the user as in your workflows, and you want also to retrieve the ratings, but this time providing movie in the workflows. Well, you cannot have both user as your partition key and movies are your partition keys, because you can only have one, or you can combine, but it cannot be one or the others. Only solutions, spoiler data modeling, multiple access pattern on the same data, multiple table. Duplicating the data is the way to go. Storage is cheap. That's the trade-off to have super high performance with petabyte of data online. So here, retrieve the rating by a user, by a movie. By the way, you can notice that it is exactly the same value, exactly the same column, exactly the same types. We are really inserting the same data in 2 tables. So, okay, that's the pattern. Now you know you have 2 tables to access pattern. But you, as a developer, each time somebody changes a rating, now you have to update the 2 tables or the n tables, depending on the access pattern. To do so, you will also use the batch. So begin batch, apply, and do the batch. I think batch operations has been introduced in Spring Data in 3.x something, and it's not even as deep as here. Okay, so what the batch is doing, is it like batch update? Well, it's not. Okay, what you need to understand with batch is the target is to have data integrity into tables. They are atomic when you're working with the single partitions. Go to the partition, insert multiple record, back. If something goes wrong, the partition is not created. It's kind of a rollback. It's atomic. When it is multiple partition, what the batch is doing is triggering each statement in parallel. So the order of the batch is not important. Triggering each statement in parallel and retrying each one until everybody's success or batch timeout. So it's pseudo-atomic. Now it's very unlikely that the statement failed in the first place, but even more if you retry them. Remember, we are token aware, we are doing the retries. So I'm the batch, I'm reading the first statement, try to trigger it, I got an issue, I will re-execute it, but on another replica and another replica. Now, for some reason, if after the batch timeout, one statement is not successful, the batch is considered failed. Now I'm teaching Cassandra for, 4 years, and I was not able to create a use case to demo it, so it's unlikely to happen. Okay, no guarantee. That's really the edge use case, and no rollback if something happened. But here I'm in front of you to announce with a big smile that ACID transactions will be introduced in Cassandra in 4.0, landing next year. So pretty big, and there you will have the rollback. So rollback are coming next year. Okay, that was the batches, multi-person batches, and doing batch with Java. Yes, cool. Let's do. And it's good to come prepare with all this statement one after the other. So here, how do you do batch? Here I have 2 tables, comment by user. Okay. Here you can think of, I put a lot of different use cases also for you to project, but here think about YouTube, okay? The comments can be shown by user. You are on your user page, you want to see all the comments that you have made, and comment by video, that's the comments below one video. So it's exactly the same attributes again, because a comment is a comment. But here now, user ID is the partition key for comment by user, and here video is the partition key for comment by video, because 2 different access patterns on the same data. So here I have my 2 create statements. So, and here now, if I want to prepare my statement, insert into. So far, so good. Nothing changed. I'm just getting my statement, prepare in the beginning, and now when I want to execute a batch, like create a comment, I will here, and I will execute. I will create a batch statement here, and provide my 2 prepare statements inside. And here we go. Pretty far from comment DAO .save an object. But still, this is the good way to do it. Okay, now consistency level. I will go back here in SQLSH. Remember that schema, I have my seed and 2 nodes, this time without a typo on node 2. And here I can show you in SQLSH what is the consistency. Default consistency of this guy, 1. I can change the consistency by going to quorum. So now quorum, remember my replication factor is 3. Quorum means I need 2 replica. So tracing on. Tracing on is a way to say, okay, now show me exactly what's happened under the hood. Okay, and now the same here I reuse the city by country, but I could reuse any table today. And this is everything that will happen under the hood. And so executing, preparing the statement. Of course, if you don't prepare it, SQLSH will have to do it. Single partition query. Woohoo, yeah, I provided my partition key, so no full scan table. And send Rick, okay? Rec read. So he is a replica. So he only needs to send 2 requests to the replica 2 and 3 to get the results. And get it the response, propagating the response, request complete. Local quorum. He probably did not wait for the 2 acknowledgements, even if they received them immediately. Okay, so if now going back to consistency level 1 and execute the same query, what will happen? Well, this time he is a replica. He doesn't even have to ask his neighbor about something else. Consistency is 1. As long as the coordinator can reply, I give you what you need. So it's the fastest. And, long story short, you see how many steps are needed if consistency 1 and consistency all. So when you build your app, default local quorum, single DC quorum, multi-DC local quorum. That's the default, the basics, replication factor 3. Now you can ask, this is an IoT query, I need to write as fast as possible. 1 is enough, local 1 is enough. Okay, sure, if somebody come and read the sensor data over the day, at the same time, he will miss 2 milliseconds. Is it bad? Yes, no. You can make it work. Also, even if you are writing with 1, you can still ensure immediate consistency. The read will be consistency all, because then 1 plus all meaning the 3 node, you get 4, it's bigger than the replication factor, you're good to go. But you're also at risk, because this read query will be focusing more on consistency than availability, and if you lose one of the node, this request will not work. So make sure to put quorum, local quorum as a default, and then for queries, think about it. Do I need to change it? Okay. Lightweight transaction. So those are for the race conditions. So as of now, in each time we insert, it's an upsert. I told you no integrity constraint, no read before write. You can change that. Monzo bank has communicated to run only on Cassandra. So to run a bank on Cassandra, you would probably need some kind of performance transaction, right? So here you go. So it's called the lightweight transactions. So here I create the table, sample lightweight transaction. That's the name of the table. And here, insert into Dragon Slayer, Joe, if not exist. Okay. Get was applied true. So the insert was successful. If I doing here the same, Dragon Slayer is my full primary key here, if you look at that. So if I try to insert something, default behavior, it will replace, but here if not exist, was applied false, and this time it gives you back, hey, I was not able to do it, this is exactly what's existing in the table. Now your job to decide what you want to do. And if now I select, guess what? The value will be Joe and not Jen, because the second statement has not been executed. So what do we want with that? Here a sample for you is working with passwords. And also I can even update the time to live at 3,600 seconds, which is an hour. So here, look at that. We have a password and a reset token. So here, put back the how many record, 1 hour duration of one record. And here I'm putting some reset token here. Devox developer would like to reset his password. I generate a reset token. Okay, send the reset token my email. And oh, he clicked on the link to renew his password and is updating, putting back the reset token as null and the password as the new value if the reset token is what is supposed to be. So somebody just was applied true, and guess what? Reset token is now null, the password has been encrypted, and the second, or you came back and click again the same link to reset your password, because this is what we keep doing, right? And you get an error that token has already been used and was applied was false. So the second one is here. So was applied false because it was already done, and the malicious password cannot be reused. Okay. Now, what about the Java code to do so? Lightweight transaction. So not a lot to say. It's really just reusing if not exist. So here, drop table, create table, truncate table. We saw them. Create user if not exist. That's really going to this statement. Okay, show me my statement, my friend. And this is why it's also pretty neat to use this query builder. You just have to add in your builder pattern if not exist, and you're good to go. So here we are doing read before write. And if not exists, we are doing a transaction. It's a distributed transaction. When you start doing distributed transaction, and distributed logs, you open a kind of worm. So here, under the hood, we are using Epaxos transactions, Epaxos consensus algorithm. So that means we will have to contact both of the nodes. Do you have the data? Lock both of the nodes, provide the value, and validate everything. That's 4 round trip. So LWT insert will be at least 4 to 5 times slower than the regular write. And as people using Cassandra is all about performance, low latency, write millions per second, every LWT count, so use them, but only when it makes sense. Okay, let me run that, but I would rather keep moving. Okay, did I hear? Yeah, it's coming. Just taking forever, okay. Yeah, that's for me. I love this green bar, don't you? Okay, paging. Select star from your table is not a good idea. I keep telling you that. But if we did not put any protection or guardrails mechanism, select star from a table, best case scenario, out of memory of one node, worst case, I would say, best case scenario, your application is out of memory, worst case scenario, the node is out of memory. So every query in Cassandra is paged. Default page size is 5,000. And better to show you the code about how to handle the paging. Okay. What are you doing the first time you create a CRUD repository with Spring Data? Find all. Don't do that. Because find all will exhaust every single page. Okay. For dev, it's okay. And of course, this is when you are running into production that you're running into troubles. So find all should be annotated forbidden, in my opinion. That's really, really something you do not want to do. And the issue is it's the method with no parameter, donc it's the first one you want to use, right? Yeah, for test, that's okay. Okay, so here we are dealing with paging. So here we are running a batch statement, putting 50 statements just to insert 50 item in a table. So here, batch statement execute. And then we will create a statement. Remember my statement? So here this is a sample to provide your consistency level, your paging size, and your timeout. And here I got my result, page 1. So when you execute something, what you got back is a result set. In a result set, you find some rows and metadata. The metadata will contain if it was applied or not, what we see for LWT. The response time, it's provided to you there, and the information regarding the paging. So I got my page 1, get my result, available without fetching, so I even know how many items I do have in my page. And if those items are lower than the page size, you don't have to look for page 2. So here you display page 1, okay, going with an iterator on the page. So the iterator is clever. So you are moving next. When you reach the end of page 1, the drivers will go and fetch page 2 for you. This is why we say get available without fetching. So if you put some limit here, going next, and do not go beyond page 1, you will not fetch page 2. And this is just what I would like to illustrate in this code. So here, so execute page 1, list what I do have in page 1. In the metadata part of the result, I'm reusing the paging state, which is a byte buffer that I like to convert to Xstring. And here I putting back my paging state. It's the same simple statement. I just now provide the paging state, and when I re-execute it, it will go and search page 2. And this is how you do page X. So the paging state will hold kind of a cursor of where you are in your data set, and also the timestamp when you execute the queries. If some data are put after that, they will not show up because the paging state is a state including using timestamp. So you can query at exactly when the query was issued, even if more data has been inserted in between. So executing the paging, but really the code is more important than executing. Okay. So here we go. Table created if needed. Yes, inserting 50 items using the batch. Okay, done. Page 1, I got here, and page 2, but I did not list the page 2. Yeah, here is page 2. So again, no need to exhaust the full table if you just want to show the first element to a user in the user interface. Paging and sorting repository. Okay, all right. So far, everything we did was synchronous. We provide the parameters, we prepare the statement, we bind the statement, we execute the query, we wait, and wait, and wait. Come on, it's Cassandra, so we wait, and it's fast, and we get the result. But we are stuck. The thread is blocking during all that time we are synchronous. So instead of executed statement, go execute async, or use the... So now you prepare your statement, bind your statement. Or you, instead of execute, you do execute async and get a completion stage. And then call back for you to process that. You get callback per page. So that's your work to then compose if you want to keep going over the next page, or put a big page size. But here we are working with async result set. Okay, good. So asynchronous, super good, doing some queries in parallel, having a couple of futures going, and synchronize just to get, instead of in, for instance, just fire 2 async queries and keep going when you have both results. Completion futures dot all complete. But it's not good enough. Debugging some asynchronous queries can go to callback L. What about if the first statement failed and not the second? How do you catch up? There were triggers in parallel. You need to eventually execute a query to compensate what has been done and should not. So what can we do better? Well, this is here the reactive queries. So here you prepare your statement, as usual, bind, and now you execute reactive. Okay, and you get a flux. The flux is a subscriptions. And now you get a callback, not for each page, but for each row. And if for some reason your application cannot keep up with the throughput, Cassandra and the drivers have a back pressure mechanism for you to keep going, to be able to process that, and when it's done, on complete. At the drivers level, we implemented our the reactive specification with the publisher, the subscriber, the subscriptions, using the TCK, which is a toolkit for validating that your implementation is fully reactive. But doing so, now the object that we return from the reactive drivers are a publisher. And so if you want to use a reactor and convert that in Flux to be compatible with Spring Data Reactive, you can. But if you want to use Quarkus and want to use Mutiny and get your single working as well. So Quarkus Reactive, Spring Reactive, and the Micronaut reactive part as well. It's sort of a matter of casting those publisher, just the spec, into those Flux Mono, Unilist, not list. But this is how you get it. So code, yes, let's go to code here. So asynchronous programming. So here, as usual, prepare my statement. Okay, nothing changed, exactly the same statement. But now instead of execute, we do execute async. And starting working asynchronously with the then accept, compose, create. So here, accept, compose, accept. So before I told you, there is no joins, n+1 select, not what you expect. Well, these asynchronous way of thinking is more balanced here. I can list all my groups with a first, and then compose, and for every single of my user retrieve or group retrieves, fetch the list of users for this one, and then flat map, get a single stream, and be happy with that. So that's n+1 select could be done through these parallel asynchronous queries. So here executing async, user async just, yeah, nothing special. Delete user async, find user by async. Oh, yeah, maybe I should just hide. Yeah, here, I don't know how you test asynchronous method with JUnit. I created my own superclass where you provide a predicate, and it will do the assert for us. But here, I put a big warning. I did not put any assertion here. So this is why here I put a get, just to have my unit test running. Okay. Don't hate me. But now there is no easy way to run some asynchronous tests in JUnit. Instead of having these apply async, get your results, and on the callback to your assertions. Okay. And go to reactive and go. I mean, yeah, nothing special. Create reactive, update reactive, no. Okay, and same with reactive. So very similar. Instead of exec async, you will get exec reactive. Okay, so exist user reactive. And here I got my reactive result set that I can immediately convert as a mono. So pretty convenient reactive result set, and you can convert as mono or flux depending on you get a single result or multiple result. So here default is empty. So here, yeah, query all user. Here you have a sample of converting as a flux. Okay, so here prepare statement is the same, just here convert to mono and flux when it's needed. So should you use reactive in your app? If the rest of your app is asynchronous, sure, of course. Now, as soon as you put your fingers in the reactive world, everything needs to be reactive. So I got burned a couple of times with wet flux. Because now each time you get any blocking code, you're just stuck. Not anymore. The kind of fix, or you can at least gracefully shut down this behavior. But does it really provide you a performance boost comparing to asynchronous? Yeah, my benchmark. Not so obvious. What is neat would be the reactive and back pressure mechanism, and also the code, because if you look at the code now, it's really look alike some synchronous code. You have both the speed of async, but you can still work on these reactive. Also, how would you do paging in reactive in each time you get a callback for each record? Well, you can do that by using skip and limit. So you just get it and get it only what you want. It's not but even in paging and sorting reactive, you can already do some paging with reactive. So you need to exhaust your list. Did I execute this guy? I think I did not. Let's do it. And keep moving with object mapping, and then back to little slide because we still have some ground to cover. But we are good on time. Okay. Reactive. Okay, and again, block is like the get for completion futures to get you a blocking code to pass your test. For reactive, testing reactive, this time I totally admit I'm using the client for Spring. Even when I'm not doing Spring, it's just super convenient. Okay, data object mapping. Wow, that's a big one. Inside the drivers, you have object mapping. You don't have to reinvent the wheel. How does it work? It works as an annotation processor. You will annotate entities, DAO at compile time, stub mappers implementation are generated, and will be used in the code at runtime. Sounds familiar? Who's doing that? That's exactly the way of thinking of Micronaut. So you annotate your entities like that. set of annotation from the drivers, not from another framework. So it's done by the drivers. Entity, partition key, clustering colon, get the name. I think it's pretty obvious. Now insert your interface DAO. That's what we want to do again. Not really implement the statement, the code, everything by yourself. You can use this DAO and just select query, provide a custom where clause, as you can see here. Oh, super familiar, right? Yep. Insert, delete. And if you need to provide your own implementation in some code, you can always use some query providers and do your own stuff. But to me, those DAO is like any CRUD repository. Create, read, update, delete for the entities. But when it comes to doing lightweight transaction, batches, insert JSON or whatever, I have my own class close to that, okay? It's not silver bullet. Annotated mapper, so this is how you map your DAO to your one mapper per application, and in the mapper you can access all the DAO you define with the name of the key space for each and the factory. But better show you a code again then. But it was still neat to have these in big screen. Here I am. So here what I do have. Remember our comment by user and comment by video? See? The same class, it was here, schema util, comment by user, comment by video. How would you do that with object mapper, right? It's the same object. It's the same object. So this is how you do. You get a parent class comment where you provide all the column name. By the way, it's if the name of the attribute of the field match the name of the column, there is nothing to do. It will be done for you easily. Now comment by ID. This is where you say, oh, comment by user will be connected to comment by user table over here. I'm extending comment and I'm just overriding the partition key. And video, same, but here I overriding the video. Now I do have two bin, but my comment DAO, okay, will just get retrieve users by users comment and video comments with these two different queries. What about the upsert and the delete? Well, this time I need to have a batch. DAO cannot provide a batch. How do you do? Here I use this query provider, which is concrete class implementation. And in the query provider, this is where you find prepare statement, prepare statement, and execute my batch. Okay, oh, it's a retrieve, so I just need a select. But here, upsert, I will then create my batch statement. So here is what I would like you to realize is I know I have two access patterns to the same data. So I duplicate the tables. I have two bins. And I can either use two DAO or group in the single DAO if you wish. But you still need to do all these batch operations. And when you insert a new value, you need to write into both tables. So to do, you need a batch, and you need that way to do a batch. And what I would like you to stop doing, or people doing, is, oh, let's create an object annotate the object. Let the framework create the table associated to the object. That's great for the first day. But the second day, the business came with the second access pattern on the same data. What you have to do is create another table and another bin, as I explained. But what people tend to do is reusing the object. After all, it's called comment. Try to execute another queries with a different access pattern on the table. Get the error message. You are not executing any query on the partition key. It will fail. Look on Google and just annotate allow filtering. This is what happened most of the time. And the allow filtering, it's working on the machine, go into production, the request is terrible, taking 10 seconds, and of course that's a Cassandra fault. No, it's not. Okay, big takeaway of object mapping and what could go wrong. Speaking of data methodology, what is the good way to do some data modeling with Cassandra? I show you tables with multiple keys. I think you now have a good idea about partition key and clustering key. So what is the overall methodology? In relational data model, you start with the data, MCD, conceptual data model, get all the constraints, go to the third normal form, and only then give that to the developers, and developer needs to figure out from the business needs and the existing data model which kind of join will work, and if it's not exactly what you expect, what kind of index should you put, and then ints. Long story short, that's your job to match the business needs with the existing data model. And you do that because the data model you are using is normalized. The data is used once, and you have integrity constraints, and joins, and foreign keys. In the NoSQL world, so in the SQL world, multiple database family, JSON, MongoDB, Elastic, CouchDB, column-oriented, that's Cassandra, DynamoDB, HBase, Graph, Neo4j, Titan Graph, and key value, Redis, and all the cache. So here we are talking about column-oriented, the one with tables, Dynamo, Cassandra, HBase. Those are using denormalization. It's a bit like data mart. If you have used some data warehouse and business intelligence, what you do is you create the join when you save, not when you read. So instead of having a table user and a table group and doing the joins when you read, you have a table called user by group, and it's a single table. And so if you need all the user for a group, user by group. But if you need all the group for user, it's a second table, group by user. Data is duplicated. The join is done when you save, not when you read. You denormalize your data. So when you denormalize, you tend to add a lot of columns. It's a flat model, if you wish. You can squeeze multiple joins in the single table if you want, duplicated the data as much as needed. That's the way to do. Cassandra, very easy to save very large amount of column, and having scarce data set with empty column, totally fine. If you add a column to an existing Cassandra table, it's immediate, because it will not try to insert null in every single existing record, like some relational DB would do. So scarce data set, denormalize. Pretty cool as well for training a data set in machine learning, actually, because you can have super wide tables. What are the physical limitation? I think it's 2 billion columns, because the only very hard limit in Cassandra is 2 billion cells per partition. So single row, 2 billion column. So that's a lot. So in the NoSQL world now, you need to know the queries. You need to know the access pattern, because data model MCD is not enough alone. With the entities plus your access query, only then you will be able to get what is your exact data model. So this is the methodology, so implemented by Dr. Shedboko. That stated, okay, to create your Cassandra data model, you need the MCD, you need the application workflow, you will implement a couple of mapping rules to get you the logical data model, and optimization rules to get you to the physical data model, then go back, you got your Cassandra query language statement to create the tables. So here, if I'm going back to this IoT data model that I keep talking back in multiple samples. So here, start with networks. You are a company with multiple networks, the networks of sensor in the forest, the networks of sensor in the volcano. So one network has one too many sensor. Then in a sensor having its own characteristic, you will have, of course, multiple records over time. MCD, network, sensor, temperature, attributes, easy. Queries. Okay, what does my application look like? First screen, I would like to get all sensor network, because I would like to see my different zone where I do have my sensor. So first screen, I want to see forest, volcano, such. So select star from network. And then I would like to display all the sensor for a network. Okay, so this one also. And then show the raw temperatures values for a sensor, that's Q4, or display a heat map for the network. So having the temperatures for the network, so for the sensor. So here you have two joints to squeeze in a single table. Oh, did you notice? 4 queries, 4 tables. Okay, so now the mapping rules. Based on entities and relation, you will create tables. So here, network, sensor, temperatures. Okay, then on which column do you need to do your where clause? That will be your partition key. Okay, then does it ensure unicity? Yes, no. What do I need to add? Is there a range clause I would like to do? Those are your clustering column. And then you can say, oh, if I want to see all the video, all the comments on my video, do I want to see the last first, or and you will decide how you should order, descending and ascending. And so this is what it looked like. So temperature by sensor. Okay, so I want to see all the temperature of the sensor. Then my where clause would be on latitude, longitude. Okay, that's my partition key. Is it enough to ensure unicity? Of course not. You need that timestamp. Okay. Do I want to store my timestamp the latest first or the latest last? That's better to get the latest first, because what you want to have is the latest value recorded by the sensor. And here we go. Here we got the order. Okay. And then you add these, you want to get the data for sensor. So you add back this sensor cluster and column. But what you want is the heat map, right? So you will look for this latitude, longitude. Okay. So, do and don'ts. Follow Cassandra data modeling and not relational DB. Do not reuse the same table for different where clause. I think now the message is pretty clear. So know your request and schema, data model before the code, SQL before the code. One table, one access pattern. Most of the time it's one table, one query. Now in some case I say one access pattern because you can have different inequality, different filters. Duplicate the data. Storage is cheap. That's the trade-off. That's the trade-off to get you performance with petabyte of data online. Secondary index, did not talk much about it. You can also place some index in Cassandra table called secondary index if really you want to search by the colon, which is not part of the partition key. Create an index there. But they make sense only when the cardinality is low. So what is the cardinality? Is in how many partitions you will find the value. Okay, so if maybe I can find a sample here. Yeah, maybe cities. Maybe the cities would be good. City by country. Okay, so here, if you look at city by country, you need to always provide the country to request because it's your partition key. Now, some could decide that maybe I would like to request by city without creating another table called blah blah population by city. Because I consider that my city will not appear in a lot of countries. I'm just switching here. It's almost 1-to-1. So now if I look in how many countries is my city, probably 1 or 2 if we have homonyms. So the cardinality could be considered low. And then secondary index on city here could make sense. But sometimes it's a value which is very common. And if you try to create the index, it will take forever to retrieve because you will have to look up for the value here and then look in any partition to get you the data. Okay. Materialized view as experimental, so this one, please do not use them yet. Okay. It's also a way to create views based on a select on a table, providing another partition key. The issue with materialized view is they are not consistent. We cannot guarantee you that what you are actually querying in the materialized view reflect what we do have in the tables. It's updated asynchronously, so this is why we told them experiment. We cannot guarantee the consistency of those materialized views. Now again, some user decided that this data is almost never updated. So I will create materialized view to provide different access pattern, even if I know that it's not the more up to date. Again, what we want to do is creating multiple tables, one per access pattern. Okay, data modeling. Here I would like to show you the same pattern that we have done right here, but with a little tool that we implemented. So it's also eventually for you if you want to know more about Cassandra or stuff like that. So again, reusing the Gitpod platform, we're kind of fond of this technology, so your ID in the cloud. What we did here is we created an extension to help people taking some courses, and this is what it looked like. So it's still an ID. You know, you don't realize it's an ID. It's still an ID. So I can go back here, and it's VS Code, so I can check my code here. But here, I can go here local. And here I will start a Cassandra node. I don't know if you have seen Katacoda before. It has been acquired by Array, so it's not there anymore. but that's the same principle. It's some training, and here you just have to click there. The command is executed on the other side. So it is pretty convenient for any Kubernetes training. So in here we have just a sample for the data modeling, sensor data modeling. But during the time it started already. So SQLSH over here. So here I create the key space. I use my sensor data and create the different tables we just discussed. So it's easy. Sometimes it's just too easy here. And here I'm loading some data and showing what's there, and retrieving all the data sensor data model. So this sample is part of data /learn/. Okay, it's not the ads pose, I assure you. That's data modeling by sample. Data modeling Cassandra is almost some considered by methodology and also some art. Here, full-fledged data modeling, okay, by Cheboko, Dr. Cheboko it's himself. So sensor data modeling, message data modeling, digital library. We have e-commerce, time series, investment portfolio, and order management. And each time, like for the sensor data modeling, it explains you the concept, the queries, the methodology, and then you go into the hands-on part that I've shown to you. Okay, that's by practice. Oh, wow, okay. I will move fast on this one, just realizing that I took too much time on one thing. So you have a relational data model. You want to go through Cassandra. How do you do? So each time you have multiple challenges, you need to move the schema, the code, and the data. First, easy offline migration. You just move the schema in Cassandra using the methodology. So the schema will be different. You migrate the code, and so you have to change the code to match the new schema. Okay. ETL, it's offline. Okay, so ETL, you transform the code to match the new model, and you open the new function. It's offline migration, no brainer. But this is not what we want to do. We want a zero downtime. So first one to do it is shadow writes. So this time you move again the schema, you move again the code, but here you open your new system to do the read and writes in shadow, just to see if it's still working. So you test the writes, and everything is ready. You just test the reads, and if you're happy, you finally can shut down the functions. Okay. And here what we tend to do here, moving from SQL to Cassandra, or for moving to an old version of Cassandra to a new one, we are doing the dual read mechanism. So this time, migrating the data model, migrating the function, making sure that now when you do the read, you are using both systems, and when you do the write, you are using the new system. You can do the migration of the historical data with ETL, and finally you can. I just have an animation. Finally, you can just open the read and writes in the new system. Simple as that. So here is the relational data model of Pet Clinic, Spring Pet Clinic. So and I use the methodology, say some entities accessed by the keys, I can reuse the same table, just changing the partition key. Create, read, update, delete, it's good enough. One too many, sometimes one too many, I can use a list set of map. Sometimes I cannot do that because both have attributes, and I will squish into a single table, pet by owner. or owner by pet, depending on what I want to do. And when I do have many to many, well, I need to do, when I have two tables, user by group and group by user, when I do have an association user group. And this is what it looks like. So why I do show that? Because the Spring community have this dedicated organization called Spring Pet Clinic Community, where you can find the implementation of the traditional Spring sample apps, Pet Clinic, implemented in multiple ways. What I did the conversion, and there you find a way to implement with Cassandra full reactive. So using Webflux, Stack, Reactive repository, and Cassandra reactive drivers. Okay, so let's go into more code. More code quickly. Okay, here we go. No, what I want is my ID over here. Okay. Let me close all that. Yes. Okay, so first, Spring. This Spring is pretty easy. Okay, so you want to use Cassandra with Spring. You will use Spring Data Cassandra, two flavors, Spring Data Cassandra, Spring Data Cassandra Reactive. First providing you the Cassandra repository, CRUD repository, and the second providing you CRUD, the reactive CRUD repository. So when you want to create a repo, okay, extend Cassandra repo, you create your entity, you annotate your entities, this time with the Spring Data annotation set, not the mapper annotation set. It's a different set of annotation. So here you got the same, pretty close, primary key, colon type, annotate my entity, right? And getting my repo. Oh, okay. But I keep saying you that as good as repo can be, I have so many use cases where it's not enough. I need my batch, my LWT, my lightweight transaction, and so forth and so on. How do you do? Well, in Spring Data, you have two things. The first thing is Cassandra operation. Cassandra operation, it's the low-level object. This is where you can access the SQL session and have the full-fledged access in the drivers. So in your unit test, you can inject directly Cassandra operations. Here it's a Spring Get Boost test. And doing so, you can execute a select. Here, directly Cassandra ops. You can also do batch update, batch apply. You can also directly inject SQL session, because guess what? Spring Data is based on the drivers. The three, okay, no suspense. But with Spring Data, you also have something that is not well known. Instead of creating an interface, extending Cassandra repo it's an interface with nothing. What you can do is create a concrete class extending simple Cassandra repository. And it's doing all the difference. You still have the save by ID, find all, implemented for you by that stuff. But on top of that, you can inject and have access to the SQL session. And with that, you can do what I did before with the query provider. So this time now, if I need to update multiple tables with the same data, this is how I do it, because now with the simple, I do have access with the implementations. When it comes to the configurations of these Spring Data, if you put application.conf in your app, as I told you, the configuration is used. Now what you find here is the Spring Boot application. And Spring Boot here I use Spring Web, so not the reactive one, Spring MVC, just to get REST API, super classic. And here I use Spring Boot Starter Data Cassandra. So access to this Spring Data repository in the Spring Boot context, of course, and also these subsets in the dedicated namespace in application.yaml, where you do have access to some keys and some completion here for you to use. So here you have some keys here, but probably 50% of what is possible. This is why in the beginning I told you about this application.conf. So Google application.conf datastax driver, you get the full list of hundreds of keys. So have a look about what's possible before going into production. Notice here you can still put your timeout, consistency, and page size. All right, so what can I say? Yes, for this demo here, I used Spring Data M3, so Spring Data 3, Spring Boot Data 3, because it's the only one that you should consider to compile your Spring app as native. I tried with 2.7.4. I had to tweak my native Maven plugin a lot to make that work, whereas in Spring Boot 3, you got it right. Spring Boot 3 required now GDK 17. That's a big change. And Spring Data moved to Spring Data 4. So, get ready. So here what I can show to you in this app. Okay, yeah, just test. So here is initialization of context using the repo, operation using the controller. But here what I would like to do now would be to compile that as native, just checking if when it start downloading, that snapshot. Okay, so Spring Data Cassandra, compile, download, the validation stuff, yes, Cassandra repo. Yeah, I think I show you what I wanted to show you using Cassandra. Yep, so here is the Spring Native, and the slide for you is don't let Spring Data Cassandra creating you the session. Create your own bin and define your own attributes. You know what's there. Do not let Spring Data Cassandra create the schema. See in the code, just before I had this create if not exist, and I was lazy enough to use it here, create if not exist. No, I mean, for dev, maybe, but for production, you need to create your own data model, your own SQL. N+1 select, so don't use in, eventually use asynchronous queries. Please do not reuse the same object for multiple access pattern, and do not only stick to the basics and simplicity and obvious of Cassandra repository, CRUD repository. There are so many opportunities and things to know to go beyond. It's written in Spring Data docs. Okay, nothing to complain about. It's just who reads the docs, and it's stated front center. Use Cassandra operation first, and only the repo if you if you really have to. Okay, 5 minutes left. Let's go into code with the 5 minutes. Okay. The code is the most important. So let's go into the code. Okay, so Quarkus. With Quarkus, you have a data layer implementation called Panache, which you can do both a repository and active record when you define some entities and can directly save the entities. With Cassandra, they just decided to reuse the drivers So Quarkus is easy. Yeah, let's reuse the drivers, right? We had to implement at DataStax a little hope, a little bridge to make that work very, very well, as described here. This Quarkus extension make sure that we could use mutiny type in the reactive, work well with the native image support, and also be part of the vertex event loop. So not a lot to say here. If you look at the implementation in Quarkus, what I just did is actually reusing the driver's code. And when here I provide you two implementations. So first using pure SQL, as I just keep showing you from the beginning, and one with object mapper, still using the drivers. Here you have a REST controller, injecting directly the Quarkus SQL session. For Micronaut also have a data layer called Micronaut data, and guess what? They make the same choice, just reuse the drivers, not reinventing the wheel. So this is also why I took so much time with the drivers, because I knew this is where I was going with Quarkus and Micronaut. So here you can directly reuse the drivers. I told you just quickly in the beginning that the philosophy with Micronaut is using some annotation processor. So doing a lot of work at build time, looking at annotation to generate the needed code. And so the object mapper is actually part of the annotation processor list that you find in Micronaut. And put it at top just to generate my stub class first over here, and let's Micronaut do its magic. The code that you have here in the repo, Maven clean install, Maven clean package -p native, work with the 3, so you can compile it in native in the 3. But with the 2 last minutes, because here is a code, I can show you that it's working, it's running. I still have some disappointment. I need to find back my slide now. I have too many stuff open. Yeah. So doing all the work and everything, and you compile 3 native images, you're super happy it's working. So you say, yeah, let's put our micro image as a container, put that in, and put that as a function, as a service, and deploy it. Well, we do have a big issue. The native image takes a couple of seconds to start. Not microseconds, as you expect, like 50 milliseconds. With Cassandra, because the drivers need to contact the points and the contact points and need to open a connection with every single node, it takes almost 2-3 seconds, even on a 3-node cluster, to start. So it's not good enough for class native. It's not what you want to do. What can we do? So the next generation of Cassandra drivers will use a gateway, a proxy that you put on inside a Cassandra cluster. It's a node of Cassandra without the data. This node exposing you stateless API, REST, GraphQL, Rust, and mostly gRPC. So depending on your use case, you have one API you can use or the others. But here, more technically, this is what it is. Now, instead of using the drivers to do all the load balancing edge case failover, you are leveraging gRPC capability of failover, load balancing, translating, and it's not stateful anymore, it's stateless. And if you introduce this Stargate node, Stargate is open source, Stargate.io, no, I'm not selling anything here. Stargate.io, so you introduce some node in Cassandra with no data, expose API like that, and now the cloud native image took the 30 or 50 milliseconds you expect to start. Because now it's stateless and you don't have to validate those connections at startup. And now it can be truly native. Okay, so this is what we realized by implementing Stargate. We even split Stargate into a smaller runtime, only if you want to start gRPC or GraphQL or REST or whatever, you can, and you scale only what you want. Why do we want to go to cloud native so much? You know, I mean, yeah, it's the future, but well, I told you in the beginning that we make everything we can to put Cassandra in Kubernetes. It scales like Kubernetes, horizontal scaling work like we like, but accessing this binary connection from outside the Kubernetes cluster was also quite a nightmare. Even if you port your application system there, it's a different namespace. You have all these ingress settings to put. It's a stateful connection, two ways. It's a nightmare. Now with Stargate, you can expose HTTP endpoint, gRPC endpoint, way easier. So why this work? Why Stargate and why Cassandra? Well, I mean, DataStax is doing support for those open source solutions I keep talking, but we also have Cassandra in the cloud. And of course, we deploy that in Kubernetes. So we had to find a way to provide these cloud native features on top of Cassandra, and this is through using these Stargate. And that's my last slide. So we are doing a lot of events, if you are more interested in the Cassandra community. So the Cassandra days, I think, unfortunately, you will be busy at Devox for the London Amsterdam one, but we will keep doing them, and Cassandra Summit is coming back next year, March 13. And with that, I may have rushed a little bit the end, but at least you have the GitHub with all the code, all the repo, the 3 app, and yeah, thank you, enjoy, and yeah, thank you.